Okay, hello everyone. Today we have Arthur talking to us about optimal transport. Have fun.
Perfect. So, welcome to this first ZUCMAP Christmas special. Like you've probably noticed the moment you came in here, when you saw the title of my talk and this fancy Christmas hat I'm wearing here, that today will revolve about the mathematics of Christmas. Okay, so perfect, but don't worry. I've heard that these talks are particularly aimed at bachelor students and that there might be some first semester bachelor students present among the audience. So I will not expect you to have any prior knowledge for this. And so let's start at the very beginning of everything, okay? So, at the beginning, let's try to summarize this quickly. Christmas is a holiday where people get gifts, yeah? Like children, adults, everyone, you get gifts. And if someone gets a gift, okay, that means that there has to be someone else or something else which has delivered those gifts to that person, all right? So up to now, that's just basic logic. I don't know if the first semester students here have already had the first logic course. So like if you have any questions so far, please don't hesitate to ask, right? Okay, so let's come back to what we've just said before. I think we're all old enough now to kind of agree that there is some entity delivering those gifts. And when it comes to the identity of this entity, now the people start with wild guesses, all right? So in most parts of the world, people will call this entity Santa. But here, for example, in Switzerland, you will hear more people talk about the so-called Christkind. So in general, there are many theories on the identity of this person or thing. I've even heard some people saying that it is actually your parents delivering those Christmas gifts. I mean, I'm not quite sure how plausible this theory actually is, because I don't know, you've probably noticed, but especially in the weeks during Christmas, you're usually quite stressed, yeah? There's a lot of work to do, there's the end of semester exams, deadlines for projects, work gatherings, and yeah, so I really doubt that your parents will have time to deliver 1 billion gifts in these times. But okay, never mind. This is a math talk, and I'm not here to judge on how much sense these theories make, all right? And in particular, this here is no claim whatsoever that I know better than all these other people. But just for this talk here, we will assume that the one delivering Christmas gift is actually the Terminator wearing a fancy Christmas hat like this one, yeah? Okay, so far everybody is following? All right, so some of you, maybe for example, the people there might ask themselves, why the Terminator? Huh? Well, the answer is easy, because he is in the title of this talk. And if he's in the title of the talk, it just kind of makes sense that he also appears somewhere in the talk, right? Okay, perfect. So now that the foundations for this talk have been set, yeah, no questions so far, I hope? Okay, perfect. So now that the foundations are set, let's get a bit more concrete. So, what do we have? We have our Terminator here, and he has gift factories in which he produces gifts. Yeah, you see some factories, and then he has homes for people who want to get gifts. Yeah, and he has to bring the gifts from the factories to the people's homes. Yeah, so first of all, he has produced exactly as much gifts as are needed, so the gifts produced and the demand of gifts are equal, and then he can hop around between those factories and those homes delivering the gifts, okay? So now we will add some few assumptions to facilitate the mathematics that will come afterwards. So first of all, we will assume that all the children actually want to have the same gift, okay? Let's say, for example, I don't know, the CD for Terminator 2, okay? I mean, in the end, of course, this is not realistic, but this mathematical model in the end can be quite easily generalized to the case where there are more gifts. Then another assumption we will need is that the Terminator, when he delivers gifts, okay, he always delivers them at a constant speed v, right? And finally, when he doesn't have any gift, the Terminator himself, he has no mass at all, yeah? His mass is 0, and we'll model that light speed is infinite, so just that the physicists who are present here also get their money's worth. And okay, perfect. So that's the thing that's the assumptions we will make. And with these assumptions, now we're going to ask us a question, is there a best way for our Terminator just to not have to say Terminator every time? Let's call him like Zen T1000, for example. And so is there a best way for him to deliver these gifts? An optimal way. Okay? And now that we've done all this, now comes the bit more serious part of this talk. Yeah? Because who says optimal way? Says optimization. Good? And so that means now, first of all, we will begin this with a short introduction into general optimization and linear optimization. Good. So, first of all, what is an optimization problem? An optimization problem is just you have a function which is called an objective function and which is defined on some set, which is called the feasible set, okay? And everything we want to know is, does this function admit a minimal value? So does this function admit so is there a value x in the domain of definition, such that for all other values x prime in the domain of definition, f of x is smaller or equal to f prime. Okay, so to give sense to this, like the function we have has to take values in a totally ordered set where you can like compare the size of values it can take. This is really the most general definition of an optimization problem. And is there maybe some... And in general, if you just have like a random function on a random set, there's no guarantee that it actually has a minimum, yeah, or that this minimum is unique. For example, imagine we have a function like defined on the real line, and here on this interval, this subinterval of the real line, and which looks like this, okay? But this point here is not included. Then this function does not take any minimum, because we would like to say, okay, the minimum is here, but this does not... this is not contained in the domain of definition anymore, so it does not contain its minimum. On the other hand, if we just have like a random interval here, for example, and we have a function which looks like this, yeah? Then it has multiple minima, okay? Because here, for example, for the minimum, it takes 2 times this value. So in general, this is like a really general definition, and we can't say much about this. Most of the time, however, it's not stated in this general way. Most of the time, the set on which our function is defined is actually a vector space, okay? The function itself will take values in R, which is like the logical, totally ordered set we most of the time will consider. And the set, the feasible set, will be defined by some equations, okay? Like functions, we have functions hi and gj, and equations of the form like hj of x equals 0, for example, and gj of x is smaller or equal to 0, yeah? Usually for these constraints, we call them, we'll take smaller, equal, and no strict inequalities, because for strict inequalities, we often cannot really hope to find a minimal value, but this is not so important, okay? This is not important, like that's just something you will see better when you have done topology or optimization. Hey, here we just take it for granted. We have this form of constraints. And if we take of this, then we can have further specifications on the constraints and on the function we have, okay? So the function, for example, so first of all, vector space. on which the subset we consider is defined. This vector space can have finite, infinite. The problems we solve will be usually much more complicated when the vector space is of infinite dimension than when it is of finite dimension. And the first one we call infinite optimization problem, infinite dimensional optimization problem. And we have the finite dimensional optimization problem. We also have semi-finite dimensional optimization problems, which means that the vector space on which the optimization problem is defined is itself finite dimensional, but we have an infinite amount of constraints, for example. Like we have an infinite amount of equations which define the domain in our finite dimensional vector space on which the function is defined. All right? And then there's like a particular class which will be important for this talk of optimizations problems, which is finite dimensional linear optimization problems. Okay? And that means that our objective function we try to minimize is a linear function with value in R, so linear functional. And all the constraints are linear too. That means that the constraints we consider are of the form, for example, if we are in a three-dimensional vector space, like, for example, constraints of the form 4x plus 3y minus 2z equals 0. Okay? This is, for example, a linear constraint. And if we have a finite dimensional vector space, a linear functional to minimize, and a finite amount of this or these constraints, this is called finite dimensional linear optimization problem. Okay? And these problems usually are particularly nice because we know that they always admit a solution, and we have some nice algorithms to find a solution. And in most cases, the solution is even unique. Okay? So like I said in the beginning, these are always the two questions we ask ourselves when we have an optimization problem. Is there a solution to the problem? And is the solution unique if it exists? Okay? And so, for example, why can we always solve a linear finite dimensional optimization problem? I will not show you the whole proof here because that's technical and all that, but I can at least give you like a short intuition why this is true. Okay? Because imagine like what do these linear constraints mean? Yeah? Imagine we're like in 2 dimensions. Okay? And now we add some of these linear constraints just to show you what it means. Yeah? So first of all, let's say the first constraint is x. So here we have x, here we have y. The first constraint is x smaller or equal to 0. That means that we only look at this part of the space. Now let's add another constraint. Y greater or equal to 0. Okay? Here we have 0. Then that means that we also just look at the intersection of this, and now with this, where it's greater or equal to 0. So this here is not allowed anymore. And now add the last constraint, for example, x minus y is greater or equal to 0. Good? So the line where x and y are equal is here, the diagonal. And all this space, this half space other the diagonal, is the space where x minus y is greater or equal to 0. So that means that we will just allow the intersection of what we had before, which is this, with this new half space. So this is not allowed either. Good? So in the end, if these are the constraints of our linear optimization problem, the domain we have is this. It's a triangle. Yes?
You mean to turn on the light?
The computer, you mean? Yeah, sorry. Okay, perfect. And wait. Okay. And so actually, if you have this, okay, you get a triangle with these constraints. And in general, the thing is, if you add more constraints in more higher dimensions, you get more complex domains. But these domains will still always have the form of some polyhedron, okay? And that's important to know. For linear optimization problems, the domains are polyhedrons. And these are compact, right? With these constraints we have here. That's for like the readers who have a bit more knowledge. For the others, it's not important. The others just have to know if you have like a polyhedron or a set which is like bounded and contains its boundary, then you can always show that a linear optimization, a general optimization problem with a continuous function admits a solution, but I will come back to this a bit later. But here, that means on this polyhedron, when we have a linear function, you can show that there's always a solution. And now, which is actually pretty nice, is that you can even show that this solution is always attained on the border of the polyhedron. And even more, actually it's always attained on one of the vertices of the polyhedron. Okay? And why is that? Because imagine you just have like a random polyhedron, and you have a linear function which is defined on this. Okay, this is a set, and we define a linear function on it. I have not drawn the linear function. This is just the domain of definition. And imagine, okay, for example, our linear function, suppose it has his maximum here. Okay? Then either the function is constant, and that means it has the same value everywhere, and that means every point is a minimal value. Good? If that's not the case, that means there is one direction where this function gets higher, yeah, where the value increases. And since this function is a linear function, that means it will increase even further until it reaches the border somewhere. And that's a contradiction, because that means that here at least you have a higher value than here. Okay? And you can do the same thing with border points. And in the end, you get that you will always find a maximum on one of these vertices of the polyhedron. And that's good. Yeah, sorry?
So what you mean is that you always have one of these vertices that is a maximum, but maybe the whole edge.
Yeah, exactly. Like, it doesn't have to be unique vertex, because, like you said, what can happen is when you have, for example, this, okay, when this is your allowed domain. Here you have x, here you have y, and then you define the linear function which projects onto x. This function has always the same value on each of these vertical lines. So that means that it has the same value here everywhere. So it admits the maximum. The maximum is not unique, and it's attained on every point here. In this case, you say that the problem is degenerate, but still, it is still attained on some vertex. Not unique, but on some vertex. And this is good, because like in finite dimension, we have a polyhedron, but it has only finitely many vertices, which means if we check them all, and we take the minimal one, then we have explicitly solved this problem. And that's nice about linear optimization problems. The thing which is less nice is that the polyhedron can get exponentially many vertices when you increase the dimension. Okay? For example, if you just think of the n-dimensional cube, yeah? In 2 dimensions we have a line, which gives us 2 vertices. Then we increase it to 1 dimension. That means we have this line, this segment, and we prolong it into this dimension. Each one of the vertices is doubled, we get 4. Then we do it in the 3rd dimension, we get a cube, 8. Then we do it again, we get 16. You see, it increases exponentially with powers of 2. So that means in general, these polyhedrons and for this, to delimit a cube, yeah, you don't need many constraints. You only need 2n constraints. You don't need exponentially many constraints. It means with not many constraints in high dimension, you can get a lot of vertices. And so that means that the algorithms which we use, although they're not always slow because they try to find the vertices in a good, tricky way. They go from one vertex to another, but like in a smart way. The simplex algorithm, for example. But in the worst case, this can still be exponential, which means very long to solve. Fortunately, there are other methods, where we'll not go into detail, which are called the interior point methods, okay? And that means somehow you have your domain, you start somewhere in the middle, and then there is like an involved algorithm which will construct a sequence which will slowly converge to the right vertex where the infimum is attained, okay, or one of these vertices. This one does not attain the solution in finite time, but it can get arbitrarily close to it, and for every error you allow, for every epsilon you allow to be close to until you accept the solution, these algorithms have only polynomial time, which is good, which is quite fast. And so that's why we like finite dimensional linear optimization problems, because actually you can solve them in this quite satisfying way in polynomial time in the dimension. Okay? Great. So, that would be it for this quick introduction to general optimization and linear optimization. If you are interested in these kinds of things, if you want to see more of this, like in more, or if you want to know the proofs in more detail, then I can recommend you, like, for example, the courses on convex optimization, which englobes linear optimization. And also, there's a course on mixed integer optimization. These are optimization problems. Like, when you have these domains, you can add one other constraint, which is not of the form of an equation or an inequality, yeah, which says that we only allow integer values. So we have, like here, for example, a grid of Z2, let's say. And actually, we only allow our intersection of the polyhedron with this grid, okay? Then this becomes a so-called mixed integer optimization problem. And these are, in general, way more difficult to solve than the usual one, okay? Because somehow, by making all this discrete, yeah, the whole thing we did before with the vertices and all that doesn't work. And often in optimization and mathematics is like that actually by making something discrete, it gets more complicated, which is a bit weird because in the first place we had all these possible values to check on, and now we actually only have way less. Now we only have a finite many of values you have to check, and still it gets more complicated. That's something you often get in mathematics, which is counterintuitive, but so these require some more involved methods. All right? Good. So that would be it for the optimization part here. Okay, so great. Now we know some tricks, how if we have given an objective function, how we can find a minimum for this function. Okay, so now we probably ask ourselves, okay, so you know how to. Okay, so now we have like these tricks, and that's great and all, but the problem is, like in the problem we've had, okay, we've had like these factories, we've had the homes, and we had like Senti jumping from the factories to the homes, jumping around between them, and we didn't have any function, right? Like now I've told you how you can find the minimum of some function, but that actually seems completely unrelated to the problem we had. So why have I done this? How can we use what I've just told you on these linear optimization problems, for example, to solve the problem we had in the beginning, right? Actually, the thing is that this problem we've had, which was just like a drawing on these slides, we have to modelize it, yeah? Which means that we have to translate it into the mathematical language. Often in mathematics like that, we know how to solve, we have some theory how to solve a particular group of mathematical problems, yeah? Some solving theory. But what is at least as important in mathematics is if you have a real problem, you have to know how to translate it into mathematical language to actually be able to use this theory in the end. That's what we call modeling, right? And so now when it comes to transport something in the best way, okay, there's something we have to understand at the very beginning, right? And that is, maybe let's start at the basics again for a moment. Imagine you have like 2 points, yeah? 2 points in this plane. Like what is the fastest or best way you'd say to transport something from here to there? Somebody got an idea? Straight line. Yeah, That's the intuition we all have, right? Shortest way, fastest, seems the best. All right. Now, let's do something a bit different. We have this circle, we have these 2 points. What's the shortest way? Like if we look at this in the two-dimensional plane, what's the shortest way to get from this point to this one here? Somebody knows it?
You're not allowed to go inside the circle, right? Or are you?
I said in the two-dimensional plane. Shortest path. I mean, yes, of course it's this, huh? Yeah, it's this, it's a straight line. But, like imagine now you are somebody you want to deliver Christmas gift from here to here and this is Earth. Like what would be the path you choose to deliver the gift? It would be rather this one, right? And why? Because you cannot walk through the rocks, right? See, that's the point. You say, what's the best way to deliver this? This is the shortest way in some abstract distance, okay? But in terms of time you take to take this path, is this the fastest way you can take? Probably not, right? And if you want to minimize the energy you need to go from one place to the other, this is not the fastest way either, you know? And so that's important. That's something, first of all, when you model, you need to know. We have so-called cost functions, yeah? Each way we could take to go from one point to the other has some cost, yeah? You need to know what you want to minimize, okay? You have your own priorities, and then you have 2 points. You have all the ways going from one point to the other. And to each of these ways, with your criteria, you could associate a cost of this way, right? And in general, something that makes sense here when you have a cost is that you will search for the way, for the path which has the lowest cost. It doesn't need to exist in any case, okay? There can be no path with lowest costs. But there's always an infimum of the costs if you, for example, take positive valued costs, right? There's always an infimum, and you can try to take a path which is as close as you want to this infimum. So that is always something here, at least, which has to be accounted for in the modelizing part, okay? Most of the times these costs, this can literally be anything. Like for every path, you can just decide what is the cost on this, right? Most of the time, they're still related to some kind of distance in a space, okay? And before I get more into detail, I will just very quickly introduce, for those who don't know it yet, what a metric space is, okay? Because who says distance says metric spaces. So the definition of a metric space here looks rather complicated, but actually there is nothing magical behind this, right? Everything we have is we have a set, our space, with points, and to any 2 points in the set, we associate a distance between these 2 points. A distance which is a positive real number. Okay? And these distances can be quite general. The only thing which is non-trivial, like distance from a point to itself is 0. That's the second thing that is written there, not the first thing. And it's only if it's 0 only if the 2 points are the same, otherwise the distance is not 0, okay? This makes sense intuitively. Also the distance from here to there is the distance from here to here. That's all pretty obvious things. The only thing we really have to take care of is if you have 3 points, x1, x2, and x3, okay? Then our intuition tells us it is faster if we want to get from here to here. It is faster to take directly this way instead of first taking this and then taking this. Okay? That's what we call the triangle inequality. So it means the distance between x1 and x2 and x2 and x3 has to be greater or equal to the distance between x1 and x3. That's literally like the only non-easy condition we have to have for our distance, and that's all we need for metric space, okay? And if we have a metric space, then we can define a notion of convergence, which is basically exactly the same definition as the one you know from probably your analysis 1 courses on Rn, right? So this is like an abstract thing, the metric space is. But for those of you who just find this is like a bit confusing and all that, you can just think of this metric space as Rn or R, and the distance between 2 points is just the norm of the difference, right? So in Rn, we have distance of x, y, is the norm of x minus y. This is a standard metric space we will always be using. So every time I write metric space, because in the rest of this talk I will use general metric spaces with some properties that the more advanced students already know, but it's not important. You can always think of it as Rn, all right? And in the same way as in Rn, we can define a notion of convergence in any metric space, which just means that like for every epsilon we have, okay, when you have a sequence for epsilon, every epsilon greater or equals to 0, there exists an n, like there exists like a rank in the sequence such that for every n after this rank, all things in the, all members of the sequence are closer to some given element y than this epsilon, right? That's just the same definition than in R, okay? And then we can also define Cauchy sequences. This is not so important, and yeah, all right. The only thing that might be of importance for the rest is what a compact set is. So we call a compact set, maybe just getting this down. So basically we say a compact set in a metric space is a set whenever you take like a sequence of elements in the set, there exists a converging subsequence which still converges in the same set. And the set has to be non-empty, okay? And in general, like also this is like a rather, this is also a rather theoretical definition, but if your metric space is Rn, the compact sets are just exactly those sets which are bounded, which are not infinitely big, and which contain their own boundary, okay? All right. So that's everything we need from metric spaces for now. And now that we have defined this distance, we can give like, we can give a cost to paths in this metric space. Yeah, because we were talking about costs before, and I've told you that most costs are somehow related to a distance. Like you can get lengths always the same way when you have a distance on a space. Okay? And now I'll show you how you get this. The definition is a bit rough, but the intuition you have behind this is just the following. You have a path, okay? And you subdivide it into very, very small paths. This gives you a sequence, let's say x0, x1, x2 to x big N, okay? And basically what we do, we just add the distances of all these small things. Okay, we add up all these distances, and this gives us a length. Somehow you can say like the length of a path you walk in the real world is just the number of steps you take. Yeah, this is approximate. Of course, in the end, we have to take infinitely small steps, like you take all subdivisions that are possible, you build this for all subdivisions, and in the end you take the supremum of these, okay? But the idea is just this, yeah? You have your paths, and when it's small, like you say it's almost a straight line. It's almost the perfect path, really, like almost the perfect path from one place to the other, okay? So that's how you can like give a length to a path in a metric space, always the same way. And in metric spaces, the shortest path if it exists, the shortest path between 2 points is called a geodesic. Okay? It doesn't need to exist, but you can always approach it, right? You can always take paths that are arbitrarily close to the shortest paths by the definition of an infimum. Geodesic. Okay? Just this word will be important at some point a bit later in the talk. Okay, very good. So now we have done some general optimization. We have done some metric spaces. And now we're ready to come back to the problem we've actually had in the beginning, in the first place, which is our delivering gifts from factories to homes problem. All right? So, first of all, like I've been talking about these geodesics, shortest paths and all that, but intuitively, when you've seen this problem the first time, I think that's not what you thought we would be talking about, right? Because what did we have? We had like these factories, and we had a certain number of homes where we had to deliver the gifts to. Yeah? And I mean, obviously, kind of the more interesting question is, how many gifts from this factory, so we have like here factory, 2 homes, or 3 homes. Yeah, we have to decide how many gifts from this to this, how many gifts will you deliver from this to this, how many gifts will you deliver from this to this, from this to this. That's rather more the thing where you thought, okay, this is what you have to decide, yeah? And actually this is kind of true, but why was it important to talk about these geodesics? Because once, yeah, our Terminator has decided to go from this place to this place. So he said, okay, he has 5 gifts, which he will deliver from here to here. Which path will he take to go from there to there? The geodesic, of course. The shortest path. The one with the minimal cost. Because if he has already decided this, yeah, it would make absolutely no sense to take a longer path. That would just like make everything more complicated without a reason. Okay? And so this is somehow the starting point of our model. Yeah? So I will quickly brush like this. And maybe just use this. Yeah? So once again, so what we have is we have homes, we have factories, so homes, factories, and we have paths relying each one of these to each one of these, okay? And now we really don't care about what these paths are actually, yeah? We suppose we have already found the shortest path from each one to this to each one to this. We have decided on a cost function, so we have decided what we want to minimize, in which way we think that one path is more costly than another. And we have determined the cost functions which are attributed to the shortest paths. Okay? So that's all already done. Yeah? And now this starts to look much more like a mathematical problem already. Because here, let's say this is x0, x1, y1, y0, y1, y2. Then here we have a shortest path. We don't really care what path it is, it just exists. And the cost of it, we call it cx0, y2. Okay? Good. And now, if I come back to the assumptions we've made in the beginning, yeah? So we've said that our Terminator, he always walks at the same speed. Yeah? And let's say he's kind of the lazy Terminator, which means that he wants to minimize the actual energy he needs to deliver all these gifts, and not the time, okay? Then we know that the energy is linear in the mass, and also since he has to walk, yeah, here there's friction and all that, so it will also be linearly dependent on how long the path is. Okay? So that's the 2 factors that will count. So when he takes the path from x0 to x2, yeah, the energy he will use depends linearly on the mass and on the distance. And those are the only factors. And actually the rest we don't really care. There will be a constant, but for this model we don't really need the constant, yeah? As long as we have normalized all these costs the same way, we can just assume, I mean this is a model, but I just want to explain why this cost would make sense here, for example, that this is just the distance between x0 and y2. This is the cost. And the energy he uses, let's call it energy from x0 to y2, when he takes gifts of a total mass of m from one to the other, is just m times this cost. Okay? And so we've said that he has no mass himself, so he basically just can go, when he has delivered a gift, he's infinitely fast, so he can just go from there to any one of the factories in no time. It doesn't cost him any energy. So in the end, when he has delivered everything, yeah, the whole cost he will have needed is just the sum over all these, okay? So he transports a mass from this to this, is multiplied by this cost, a mass from this to this, multiplied by the cost of this path, and we sum them all. So what do we get in the end? We get our cost is the sum over all I and j from the cost of the path from xi to yj times the mass we transport from xi to yj, and we call it mij. Okay? This is how we've constructed a function we want to minimize. A cost function. And what's good about this function? We want to find the optimal values of this. These are just constants, they are fixed. We have already computed what the costs of this path are, okay? He can only decide on the masses, so we can vary this. And in this, just in these values, this function is linear. Good? Now, of course, we have some constraints, which are that here, okay, here is the demand of gifts. Let's say demand of gifts here is D1, D0, D2. All right? And here we have an offer, which is O0 and O1. Okay? And in the end, what has to be done is that the mass transported from here to here and the mass transported from here to here has to be D1. Okay? So we have a constraint which is, so the constraint is mass from 0 to 1 plus mass from 1 to 1 is D1. Okay? And then we have another similar constraint for every one of these. Yeah? So the mass from here to here plus the mass from here to here has to make D0. And the same here, so we get 3 constraints here in this example. And on the other hand, like the mass which has been delivered from here to here, from here to here, from here to here, on the other hand, yeah? So M0 to 1 plus M0 2 plus M0 0 has to be O0. All right? Good. And so here we get another 2 constraints. So here we have 3 constraints, here we have 2 constraints. And we have a last constraint, which just tells us that the whole mass here is like the whole mass of gifts. Let's call it M plus O1. And this is also the whole mass of gifts which has to be delivered in the end. Plus Y2. Okay? So here you get 7 constraints. But what's good about these constraints? They're all linear too. So what we have here is a linear optimization problem. Okay? We have seen in the beginning, in our part on linear optimization, that a linear optimization problem like this, which has only finitely many variables and finitely many constraints, can be solved, and probabilities are even high that the solution is unique. And there's also a polynomial algorithm to solve it. All right? So all that is good news for Terminator. Yeah? But, wait, what time is it actually? Because, oh, okay, I see. Good. So, at some point, actually, we're lacking a bit of time. So what we're going to do is jump to the applications of optimal transport immediately, right? Because the point is actually, what we've done here, you've probably noticed, okay, we have managed to solve like a problem with this theory here, okay? But the assumptions I've made in the beginning, they were still quite of weird, right? I said, okay, the guy who transports this, he has zero mass, all right? So when he comes back from the homes to the factories, there's no cost at all for this. Said like the light speed is infinite and all that. And probably you've asked yourselves, okay, these assumptions sound quite absurd. And I can't even contradict, you know? Like, in some sense, it's true that these assumptions were needed to make this fit, right? To make this theory fit on that. And truth to be told is that to solve this problem, actually, today, there would be like more complicated algorithms, but which would provide much better solutions is by like considering this as some kind of interconnected graph, you know? Because, for example, if these two homes here are really close one to each other, then it would make more sense to just take two gifts, go there, instead of going back to one factor at each time, right? But these problems are much more complicated, yeah? That is like old approach to solve this, but actually transporting gifts from here to there is no optimal transport problem, actually, in the sense that in the sense of what people nowadays actually understand of optimal transport, right? So the thing is, optimal transport in the first place has been invented to solve different kind of problems, yeah. But then it was discarded for a long time because there were no mathematical means to solve these kinds of problems. The initial problem we had in optimal transport was we have two piles of dirt, okay, which look like this. Two piles of sand, okay? And there's a lot of grains of sand. And if we'd like to repeat what we just did, yeah, the idea would be, okay, we have a bunch of grains of sand here. We have a bunch of grains of sand here, which are scattered around here, scattered around here. And the idea is, find an optimal way to transporting these grains of sand to these grains of sand, just by saying for each grain of sand where it has to go. But this makes no sense, right? I mean, that's not what we would actually do. And that's what the mathematicians back then thought too. Like, this is way too complex. I've told you, like, the best algorithm to solve these linear optimization problems are polynomial. Yeah, but if you have like a few billions of grains of sand, you know, then, or a few billion Christmas gifts to deliver, then actually that's not how you would do it anymore. Like, even Skynet could not compute this in time, all right? So what you do is, instead of looking at this as grains of sand or like homes where you have to deliver these gifts to, you will replace them by a continuous way of saying how many homes are there, how many homes are there, like some home density, okay? You say here more people, here less people, and for the sand it's the same. We make our grains of sand continuous, all right? And just look at the piles of sand as these shapes here, as a total, instead of like a lot of grains of sand. That's somehow like in the idea of what we said before about this discrete and continuous linear optimization problems. Often things in the end get easier when you make them continuous. Although that means in some sense that you get from finite dimensional to infinite dimensional. But you have different solution theories. And that makes that all these problems get way easier in the end, all right? And here I'm just like making like a very quick overview. I will not go into the details of this anymore, but these things, okay, what we'd like to do is just model them as functions. Good? These piles of sand. We want to make a theory which somehow functions, which somehow resembles this, what you've just done. Yeah, but where the objects are no like points here anymore, where we have like factories and homes, but these shapes instead, okay? And who looks at these shapes, we could just say, okay, how can we model this as a function, yeah? A function on the real line, and to say how much mass we have over this set here, for example, we could just compute the area under this, okay? Which means integrate this function over the set, right? So we could model this by a function. This could, in principle, we could say, for these piles of sand, contain all the information we need. But we'd also like to generalize the theory we had before with our factories, which are still on one precise point, okay? Like just also saying, okay, we have so much dirt or sand on this point, or so many gifts. And this cannot be done with the function anymore in the same way, right? Because if you just have a point and you want to make the same approach by integrating, then in the end, you will always get 0, all right? And that's the reason why we can like neither do this discrete thing, neither do it with functions. That's the point when we need to introduce measure theory, all right? And there's a good course on measure theory and integration, like if you are interested in how these measures work and what results we have this. Like with measures, you can generalize integration theory, you know, from school, in a very satisfying way. And yeah. But you will see this like in the next years. I will not go into the details of this. All right. So the only thing you have to know, in some sense, is that with these measures, we can generalize everything we have had here, right? Also these plans, like these ideas of getting mass from here to here, from here to here, from here to here. We can make all this continuous, like these few lines, we can make like a continuous measure of this too, all right? And we can also generalize these cost functions we've had here, like these sums, just by, in the end, going from discrete to continuous, so going from a sum to an integral, yeah? And then we get a theory which is basically the same, where we get like some infinite dimensional optimization problem, but where we can still show existence of an optimal way to transport the gifts from there to there. And if we choose the right cost here, like not the distance, for instance, but if we